Hello, my name's Bob Barnett. I'm here at Niagara Falls in Queen Victoria Park near the site of the first hydroelectric generating station on the Canadian side of the river. Over here, just near the bow of the Horseshoe Falls, was the intake for the generating station. The following is an introduction to this deep wheel pit generating station. As such, it was a template for 4 other plants that were built on the Niagara River at the turn of the century. The only exception was this station was a direct current generating station.
The Niagara Falls Park and River Railway began operation on the 24th of May, 1893. The Queen Victoria Niagara Falls Park Commission, which had been established in 1885 in order to protect the scenic beauty of the land surrounding the Canadian side of Niagara Falls, had by 1892 become painfully aware of just what a costly mandate it had undertaken. The selling of water rights to this tourist trolley line was its first step towards financial self-sufficiency. As with later plants built in the park, there was a requirement that the Powerhouse architecture enhance the park grounds. Thus, the exterior of the generating station was made quite ornate. In fact, up to the time of its demolition in 1985, it remained a rather attractive park structure. On the ground in 2021, there is no sign that this generating station ever existed. The map from 1906, however, shows the plant's location. It's the small rectangle a short distance up from the brink of the falls, and located about 1 kilometer from the Canadian Niagara generating station. On September 5, 1899, the plant suffered a fire that caused serious damage. Most equipment was either replaced or rebuilt. In 1900, the Buffalo Railway Company, shortly to be known as the International Railway Company, bought out the Park Railway. They began to make plans for the rebuilding and expansion of their station, with the possibility of deepening the wheel pit. No doubt they were caught up in the power frenzy that had gripped Niagara Falls at the turn of the 20th century. The company made plans to enter the general power generation market and export power to the U.S., as well as distributing it locally. However, none of these plans were to bear fruit. This was likely a result of the fact that there were 6 large generating stations either online or under construction at that time. Each one of these was 10 times the size of the trolley generating plant. The railway must have realized that they could not produce power at a rate competitive with these giants. Moreover, they were the owners of a direct current plant, and had no experience or equipment suitable for alternating current power generation. However, the IRC did rebuild the plant with new electrical equipment. They also installed an additional 2,000 horsepower turbine. This station was a deep wheel pit plant. It was the first of a total of 5 deep wheel pit plants at Niagara Falls. There does not appear to be any other generating stations, in North America at least, that have this type of layout. The arrangement was a necessary evil forced on stations located above the falls. The concept was first developed by civil engineer, formerly employed in the building of the Erie Canal, Thomas Evershed. He had been hired to devise a means of supplying turbines to stations forced by the New York State government to be located above the falls. In order to provide a reasonable head of water for the turbines, there was no alternative than to dig a wheel pit at the depth of the falls. By the beginning of the 20th century, there were 5 of these deep wheel pit plants in various states of construction. The Park Railway Generating Station was the first of these to generate power. Water was taken from the upper rapids of the Niagara River, just above the brink of the Horseshoe Falls. A set of trash racks at the river inlet screened out ice and heavy floating debris. Past this point, the water entered a cut stone forebay. This forebay was shared with the water pumping station for the city of Niagara Falls, Ontario. After passing through the forebay, the river water entered the gatehouse. In this lean-to structure was located another set of trash racks that provided a second barrier to river ice and debris. Ice was a serious problem for generating stations located on the Niagara River in the years before an ice boom was installed at the river's entrance from Lake Erie. The powerhouse contained the electrical and the mechanical power transmission equipment. The switchboard contained devices for the protection and control of the generators and the power circuits feeding the trolley line. The direct current generators converted the mechanical power of the turbines to electrical power for the trolleys and any other lighting or miscellaneous loads needed to operate the streetcar system. The drive belt connected the generator to the mechanical power system. The powerhouse floor provided a barrier between the upper equipment and the moisture in the basement and wheel pit. The basement contained the electrical cables connecting the generators to the electrical panels and to the trolley line. The handwheel was used to control the amount of water flowing through the turbine. In this plant, power was not automatically controlled by a governor, as it typically was in most other stations. The bridge tree provided a transition from the vertical turbine shaft to the horizontal generator belts. We now move to the water connections. As the water entered the plant from the forebay, it flowed through the second set of trash racks. These removed any debris that had not been held back by the first set of racks at the entrance to the forebay from the Niagara River. The headgate provided a means of holding back water from the penstock and turbine when maintenance was required. The penstock was a large diameter pipe that directed the incoming water into the turbine. The turbine shaft, which traveled up through the penstock, connecting the runner of the turbine to the bridge tree. The wheel pit originated in the early run of the river mills as simply a pit that contained the water wheel. In a deep wheel pit plant, this pit also contained the penstock, and in some cases the auxiliary equipment associated with the control of the turbine. The control rod connected the gates of the turbine to the handwheel on the powerhouse floor. The turbine is the device that converts power in the flowing water to power in the rotating turbine shaft. The draft tube, when its discharge is submerged, allows the outlet of the turbine to operate at below atmospheric pressure and thus increase the power output. The tail race is the channel that removes discharged water from the turbine. Shown here is the layout of the powerhouse generator floor. North is to the right and below, or on the east side is the intake from the Niagara River. When first constructed in 1891, the powerhouse floor contained 3 200 kilowatt DC generators and the switchboard we have just discussed. By the end of the first decade of the 20th century, a total of 6 DC generators were in place. Now we'll turn our attention to the mechanical equipment. As we have seen, the turbines were located at the bottom of the wheel pit. The generators were above on the powerhouse floor. The power transmission involved several mechanical items. First in line from the generators was a leather drive belt. An adjustable pulley was provided to keep the proper amount of tension on the belt. If allowed to become slack, the belt would slip, reducing the amount of torque transmitted and limiting the belt's service life. The belt was attached to a drive pulley, which in turn was attached to a line shaft. This shaft transmitted power from the vertical turbine shafts to the generator drive belts. The bridge tree assembly provided a means of connecting the vertical shaft from the turbine to the horizontal line shaft. The bridge tree was a massive casting that provided a base to withstand the driving torque of the turbine located below in the wheel pit. The bridge tree consisted of a set of circular gears. The horizontal driving bevel gear, known as the pinion, is shown here looking toward the north and now toward the east of the river inlet side. The vertical driven bevel gear connected to the drive shaft, shown here looking north and here looking east. The pinion is driven by the turbine drive shaft, which travels up through the penstock from the turbine runner. The wicket gate handwheel is used to make major changes in the power output of the turbine. In the early 19th century, water wheels were commonly employed when hydraulic power was to be utilized. The undershot wheel was used when the difference between the headwater and the tailwater was small. The breast wheel was used for higher headwater, and the overshot wheel for headwater above the wheel. Water wheels were typically used to power anything from small local feed mills to large fabric manufacturing facilities. Referred to as gravity wheels, they produced torque based on the weight of the water in the buckets. Their efficiency was in the order of 5%. As manufacturing expanded and more power was required, it was soon realized that a replacement for the water wheel was needed. The hydraulic turbine would take the place of the water wheel by the middle of the 19th century. There were several reasons for this, but most important was the fact that a large drop in water, known as a head of water, did not require a wheel of the same diameter at the height of the water. The head of water is directly related to the power output and the efficiency of the turbine. These new turbines had an efficiency typically above 75%. The head is measured from the level of the headwater in the forebay to the level of water in the tail race, the tailwater. It's not our intention to go into turbine development here, but to simply put this plant's turbine into a historical perspective and show how it operated. To get a basic understanding of turbine operation, we'll begin by looking at the major turbine parts. The turbine we are dealing with here was known as the American type, mixed flow type. The turbine casing is basically an extension of the penstock that directs water from vertical flow in the penstock into horizontal flow into the turbine. The gates shown here are located inside the turbine casing. Here the casing has been removed to show the gates. The gates change the flow of water to control the power output of the turbine. As we have seen previously, the gates are controlled by a handwheel located above on the generator floor. Here the gates are seen from above, looking down in the direction of water flow. In the center is located the turbine runner. Water flows through the gates and into the runner. In the runner, the water first enters radially toward the center of the wheel and is then directed downward. It is this change in the direction of the flow of the water that produces the torque resulting in the rotation of the turbine shaft. Shown again in a cross-section of the turbine, we see the water entering horizontally through the gates. Water is then turned downward by the runner. The water then exits the turbine through the draft tube. This is a view of the interior of the Powerhouse, taken circa 1893. Originally, the electrical power equipment consisted of three 200 kilowatt generators, manufactured by the Canadian General Electric of Thomson Houston design. TH had been incorporated into General Electric in 1892. This plan view shows their location on the Powerhouse floor. The switchboard contains switches and circuit breakers used to control the electrical output of the station. This is the layout of the actual switchboard installed in this station. As an introduction, we'll look at each item one by one without much explanation, and then come back and have a closer look. At the top left corner is located a circuit breaker. Below that is an ammeter, and below the ammeter is a 3-pole main disconnect switch. The shunt field rheostat is located just below the ammeter, and next to it is the series field rheostat. There is a voltmeter jack located on each of the first 3 panels, but there is only one voltmeter for the entire switchboard. This meter is plugged into whichever of the 3 panels that need a voltage measurement. Equalizer switches are located at the bottom of the second and third panel. At the top of the 4th panel is the total load ammeter, and the total load wattmeter is located just below it. In the voltage control section are located the instruments that control the trolley line voltage. More on this later. It may seem self-evident that the more power taken by the trolley cars, the more power must be delivered by the generator and in turn by the turbine. But accomplishing this is not so simple. Let's have a closer look. The chart shows the power requirement on the Buffalo-Niagara Falls section of the International Railway Company. A similar power situation would have existed for our generating station. The lower curve, Falls Power, is for a trolley line similar to that of the Park and River Railway. A closer look at the chart from about 6:30 a.m. to 1:30 p.m. shows a curve with a large amount of variability. Between the time of 7:30 a.m. and 8:45 a.m., we see a number of large changes in power requirement. Trolley cars are starting, causing the chart to rise because current is being drawn. Then they are stopping, producing the opposite result. A closer look shows that from about 7:45 to shortly before 8, the power requirement is dropping. Then it starts to rise until at 8:15 there is a sharp drop, leveling off at 8:30. This power requires the flow of electrical current. This current is a result of generator voltage. As the current rises, the generator's internal resistance will cause the output voltage to be reduced. To maintain the trolley car's speed, this voltage must be maintained as constant as possible. To do this, the power input to the turbine must be increased to line up with the power that the trolleys require. Control of the turbine's power output is not easy to accomplish. One of the simpler versions is shown here. In modern systems, powerful hydraulic servo motors accomplish this under the control of a sophisticated servo system. The gates must be opened to allow more water to flow to increase power, and closed to reduce it. But the gates must be moved against the flow of water under a pressure from a column 60 feet high in our case. In our system, however, the turbine control is a simple handwheel that operates the turbine gates. This manual system would never keep up with the frequent voltage fluctuations on the trolley line. A clever system was in use in the IRC station that took advantage of the very large surplus of water power available at Niagara Falls. If the load on the turbine could be kept constant, then no speed control would be required. For the 1,000 horsepower turbines, this was accomplished by means of resistors which were switched in and out of the generator circuit. Let's look at the components of the control system, and then we'll discuss how it operated. As we have seen, there is a generator G located in the powerhouse that sends electric current I sub G out to supply power to whatever load requires it. A relay, V, senses the output voltage of the generator and controls contactor switches, C, to add or subtract the number of resistors in the circuit. This will be explained in more detail shortly. The current from the generator travels along the trolley line and each car picks up from I sub G the current that it requires to operate under its local conditions. Here we see 3 trolley cars in operation. They take I sub G, the maximum current the generator can supply. Now there are only 2 cars on the line. They take 2/3 of I sub G. If nothing were to change, the generated voltage would rise. However, the voltage relay, V, sensed the tendency for rise in voltage and closes the first contactor connecting the lower resistor and taking the current the missing trolley would have required. As a result, the output voltage of the generator does not rise. With only 1 car in operation, another resistor is connected to take its place. When there are no cars in operation, the 3 resistors are connected to take their place and keep the generator voltage constant, more or less. As previously mentioned, this control is handled by equipment located on the far right end of the switchboard. It should be obvious that this means of control is wasteful of energy, but we have a special case here. If the energy was not being wasted in heat from the resistors, it would be just going over the falls. The waste would be in purchase price and depreciation of a more sophisticated control system when it was not needed. The heat from the resistors could be used to heat the powerhouse. It had been reported by a person who was in the plant in the early 1920s that even in the winter months the temperature was almost unbearable.